Welcome everyone. So this is going to be a solution walkthrough to the second exam in Intermediate Micro. Same with all my solution walkthrough videos. I'm going to go through kind of slowly to show you the questions in case you want to take screen captures and try the questions yourself. This one I had a typo here. This is actually option D starts here, and this is actually option E. All right. Here's question 5, 6, 7 is the first mathematical essay question. This exam covers basically producer theory, so it's following closely with Varian. So it starts with technology, cost curves. We don't do question 8. I took that off the exam. Cost curves, cost minimization, profit maximization, monopoly, profit maximization, price discrimination, monopoly pricing. Right, there's a monopoly question. Oh, this got cut off here. These were minuses. I don't know why this is showing this. It printed better than this, but this is supposed to be minuses right here. All right. And then here's the last one. Wait, that's not the last one. This is the last one. And there's a couple more parts to it. Oh, one more part. All right, sorry. Yeah, I know that part always horrible, but I can think of no better way to be able to give you a chance to try the exam than to do that. All right, so first one, the following relationship must hold between the average total cost curve and the marginal cost curve. Well, marginal cost crosses average total cost and actually average variable cost from below at their minimums. That has to do because of the relationship between the marginal and the average. Think of like a batter, softball or baseball or whatever. Your game batting average is like your marginal. If you have a good game, it'll raise your season batting average, right? That's like the average. If you have a bad game, it'll bring it down. Well, anytime you have a good game, it raises your season average. So if average total cost, if my season average is rising, marginal cost is greater than average total cost is the answer. Firm has a long run cost function. C of Q is equal to 4Q squared plus 196. In the long run, it'll supply a positive amount of output, so long as the price is greater than. Okay, so we're basically trying to find where is average total cost equal to 0. So there's a couple different ways we could do that. One is we could get an expression for average total cost, get an expression for marginal cost, and find their intersection. Another thing you could do is get an expression for average total cost, take the derivative, and then find the first order condition. That'll be the quantity, and then you got to go back and find the associated price either way. So I found average total cost. That's going to be total cost divided by output. So it's going to be 4Q plus 196Q. And then marginal cost is just the first derivative with respect to Q. It's just 8Q. Setting these equal, I get 196Q is equal to 4Q. Dividing through or multiplying through by Q, I get 196 is equal to 4Q squared. Divide through by 4, I get 49. Square root of 49 is 7. That's not the answer. We have to find the price associated with the quantity of 7 or the cost associated with the quantity of 7. And so I did that. I use the cost function. It's actually going to be the price. Okay, fine. It's 56. Question 3. A politician facing re-election can win votes according to the following process. V is equal to 500 S to the 0.2, M to the 0.6, where S is hours of making campaign speeches, M is the number of flyers mailed. Making speeches cost $10 an hour. Mailing flyers cost 50 cents an hour, or a flyer. $2,000 available to spend. You want to maximize votes. How should the budget be allocated? So this is a production problem, but we actually solve this like a because we want to maximize votes. We actually think of this as like almost a utility maximization problem. I think I may have not written. I might have skipped ahead. I just used my Cobb. Yeah, I used my Cobb-Douglas demands, and so this is demand for good S is alpha over alpha plus beta. Alpha is 0.2. Alpha plus beta is 0.8 times M over the price of good S. That's 50. This is beta over alpha plus beta times M over PY. In this case, it was 0.5. That's 3,000. So the correct answer is B. Two firms compete in a Bertrand price-setting oligopoly. One firm has marginal cost equal to 550. Other has marginal cost equal to 5. In the equilibrium, we expect the answer is D. It's this one that got cut off, right? So or it got added on to this other one. The lower cost firm becomes a monopoly and will set price equal to $5.49. The idea is we don't need to go all the way down to $5. If we do, we're still a monopoly. We have zero profits. We can't both set price of 550 because now I've got a rival. But if I go below 550, if I go to 549, the firm with higher marginal costs is out of the market, produces nothing, and then the firm with, costs of 549 has a 49-cent profit margin on each unit, which they'll be excited about. All right, so monopoly is able to use third-degree price discrimination to sell in two markets, such that the goods sold in one market are never resold in the other. Sets at a price of 15 in one market, 10 in the other market. None of that actually matters. The price elasticity is going to be minus 0.4 in the first market, minus 1.5 in the second market, which is guaranteed to raise profits, raising P1 only. So we don't know. We need more information about costs to know if they're pricing optimally in the two markets. But here we have elastic demand. Here we have inelastic demand. Monopoly is never going to want to produce where demand is inelastic because it means their marginal revenue is negative. So they definitely need to raise the price. So we know for sure we're going to raise the price of good 1. What about the price of good 2? I don't know. They might raise it. They might lower it. It might already be optimal. But here we're interested in what's guaranteed to raise the monopolist profit. And the only thing we can stand behind is that raising your price if demand is inelastic is important. All right, if the production function is 2x plus y and x plus 2y, there are constant returns to scale. Yep, there's constant returns to scale here. You could solve that by just doubling and seeing what ends up happening. Sure enough, we get constant rate of output. So constant returns to scale means if we double all the inputs, do we get double the output? Yeah, that's going to happen here. Kids in the neighborhood can produce apple cider for their hot cider stand according to the following production process. Q is equal to x to the 3/2 if they use more than 100 units of the input. Then Q is equal to x plus 100 if they use more than 100 units of the input. Or use up to 100 units of the input is this first one, and then more than 100 units of the input requires this production process. If they sell each glass for $5 and the price of the input is $75, how much of the input should they use, and then how many glasses of cider should they produce? Well, they should use no units of the input and produce 0 cider. The easiest way to see this is the price of the input is $75, the price of the output is $5, and they're not going to be, their production process isn't sufficiently productive to transform the input into output at a way generous enough to make the $5 price sufficient to justify operating. We can look into this a little bit more deeply. So here's the output price, here's the marginal product. So the derivative here is 3/2 x to the 1/2. The wage or the input price, omega, I guess is what we should use here, is 75. So let's see, we'll have 5 times marginal product equals 75. So this is P MPX equals omega x. Would be the short-run profit maximization problem. So multiplying through, we solve and find, okay, this will tell us optimally to use 100 units of input, which means we are going to be using this. So we'll have to use this production process. But notice, now what's going to happen, it'll be 5 times 10 to the 3/5, which is basically 5 times 31, which gives us basically 158.1. But over here, we're going to have 75 or 750. So this is bad. We don't want to produce. All right, so we skip that one. Consider the following firm. It has production technology given by output is going to be the minimum of x and 4. If the output price is $1 and the input price is W, find the profit maximizing level of the input. So here's my profit maximization expression. So price times my production technology is equal to omega times x. I have this perfect complements production technology. So and then I've got the price of the output is 1, and then we don't know the price of the input. Well, we do know one thing that's going to happen is we're basically comparing PX versus WX, or omega x, right? So the cost is going to be omega x. The revenue is going to be P times x, up to 4 or whatever. And then beyond that, it's just going to be 4. So we have to think about, well, what's gonna be relevant? What's the comparison of this? Basically, price times x versus w, because let's see, we had so px was 1. It's actually x versus wx. But anyway, the outcome is if w is less than 1, less than the price, then we'd want to use 4 units of good x. We wouldn't want to use any more than 4. Sorry, I said 4 units of input x. We wouldn't want to use any more than 4 because we can only produce whatever we get as our output is going to be the smaller of x and 4. So it's wasteful to use like 5 or 10 or 20 units of good x. So the most x you'd ever want to use anyway is going to be 4. And so we demand exactly 4 units of good x so long as the wage is less than the price, or the input price is less than the output price. So if that happens, so if, and the price we already knew is 1, so if W is less than 1 or omega is less than 1, then we'll have something less than 1 times x, which could be up to 4. So something less than 1 times 4 versus the output price, which is 1 times 4, right? So profits would be greater than the expenditure is the idea. If the input price is greater than 1, we don't want to use any units of good x. You produce 0. We actually shut down. All right, so monopolist sells in 2 markets. The demand curve for its product is given by 141 minus 3x1 in the first market, 115 minus 2x2 in the second market. Marginal cost of production is 3 with no fixed cost. We can charge different prices in the 2 markets. So this is a third-degree price discrimination problem. Basically, we solve the monopoly's profit maximization problem separately in parallel. So in the first market, the shortcut is to recognize that if price is equal to 141 minus 3x1, marginal revenue is going to have the same vertical intercept, the same intercept 141, but double the slope, so minus 6 instead of minus 3. Set this equal to marginal cost. So this is marginal revenue equals marginal cost. Solving real quick, we get 138 is equal to 6x1, and then x1 is going to be 23. Over here, do the same thing. So the price, the inverse demand is going to be 115 minus 2x2. So the marginal revenue is going to be 115 minus 4x2 is equal to 3. And then solving again, sure enough, we're going to use 28 units of good 2. We find the associated prices. Sometimes the mistake you might make is using the marginal revenue to find the prices. We want to use the demand to find the prices. Prices come from demand curves. So I'm going to take this 23, plug this into my demand curve and find a price of 72. I'm going to take this 28, plug that into this demand curve, get a price of 59. Then I'm going to calculate profits. The formula I like using for profits is price minus average total cost, that whole thing times quantity. It's equivalent to TR minus TC. I just like this because this is a vertical height and this is a length. So this is a box on a graph, which I like. Okay, so I calculate my profits, fine. In part B, suppose we can't serve market 1 at all, but we can implement first degree price discrimination in market 2. What's going to be the profit maximizing price quantity and total profits? First degree price discrimination means I'm going to set prices equal to everybody's willingness to pay, so long as that willingness to pay is bigger than marginal cost. So my pricing scheme is going to be from 3 up to 15 along the demand curve. Actually, this becomes my marginal revenue curve when I'm using first degree price discrimination. No, I don't price all the way down here because this has willingness to pay or marginal benefits that are below marginal cost. So I don't produce past that point, but I can recognize, oh, this point right here is the same amount that the competitive market would produce. So I can easily find that quantity just by setting my demand, my inverse demand equal to the marginal cost and then solving for that quantity. So basically I'm going to set the competitive output and the range of prices are going to go from 3 up to 115. If I calculate profits, again, using that formula that I like, price minus average total cost is going to be 112 times 56, which is 6,272. 2 more. So suppose we're an analyst. We have the problem of assisting optimally pricing different versions of this app. I accidentally switched what was high and which was low. I mean, according to how I priced this should be low and then this should be high. Fine. I'm just going to use the labels that are on here and then that way it'll be internally consistent. In terms of grading, yeah, right. So I know I flipped this, so I'll just look for correct numbers for how people answer it. Okay, so if it turns out we can only offer one version of the app, what will it be and what will be the optimal price? I'm going to set the price equal to 8 for PH and equal to 20 for PL. And the idea is if I set the price at 8, I can sell to both person A and person B. Well, there's 100 of each type, but I can sell to both of them. My marginal cost is going to be 2, so 8 minus 2 is 6 times 200 is going to be 1,200. I could set the price at 10, but then I'm only going to sell to 100 customers. 10 minus 2 is going to be 8 times 100 is only 800. Yeah, so I don't want to do that. Same story over here. Well, no. So same profits. opposite story. So now I'm going to only set the price equal to their willingness to pay, 20. 20 minus 8 is 12, times 100 is 1200. I could set the price of 12, so it'd be 12 minus 8 would be a markup of 4 times 200. But again, same story, my profits would only be 800. So this is the optimal pricing if I'm selling them separately. So total profit is either going to be 1200 if I only sell this version, or 1200 if I only sell that version, right? Total profit is either or. It's not both. Total profit is not 2400 because they're only buying at most one version of the app. Okay. If I can support both versions of the app, what pricing scheme will maximize profits? So I'm going to set this one at a price of 8. That'll keep my type A people interested in exactly indifferent between buying and not buying. But if my type B people were to buy, they would get consumer surplus of 2 because their willingness to pay was 10. And the thing with second degree price discrimination is this price list is available to everyone and they're going to self-select. So as soon as I set this price of high at 8, then those people are going to see that, and my A consumers are going to buy. My B consumers might buy if their consumer surplus is higher than however I price over here. So that's why I cannot set the price on this one at 20. I have to set it at 18 or 17.99. Definitely not 19, right? And not 20. The reason why is if I set the price at 19, their consumer surplus, B's consumer surplus for buying would be 20 minus 19 is 1, but their consumer surplus for buying high would be 10 minus 8, which is 2. Right? So the idea is I have to set the price realizing that both consumers could reasonably buy at either version at the prices listed. And so I set the price of the one that I've labeled as high at 8 so that my type A's will buy that one, and I'll set the price of my what I've labeled as low at 18 to maximize profits, or at $17.99 to get my type B's to buy that version and not to buy the same version as type A's. If I calculate my profits, it's going to be 8 minus 2 times 100 people buying is 1200, plus 18 minus 8 is 10 times 100 is 1000. So my total profits are going to be 2200. We're better off with this because pricing separately is either $1,200 from selling only this one or only this one, right? You might have seen this and said, oh, 1200 is 2400, so it's better to do this. No, because if we're pricing separately, they're going to buy at most one version of the app, and our profits are going to be at most 1200. All right, last thing. So Rip and Good Cookies based in Wisconsin. They give free samples. Let's see, Girl Scouts are their competitor. Fine. Market demand is given by Q is equal to 360 minus 1/2 P. Initially, both have costs of 370 Q. Find the price if they compete as Bertrand firms. So in Bertrand, we're going to do price undercutting. So price goes down to marginal cost. So the marginal cost is 370. So the price would be 370. Suppose now one company invests in R&D, reduces its unit production cost to 40. What price should they set, and how's the market divided between them? So what I'm going to do is I'm going to start with my demand. I'm going to solve for P. This will give me my inverse demand. If this is my inverse demand, my vertical intercept is 720. My slope is 2. Marginal revenue will have the same vertical intercept but twice the slope. Set this equal to 40, which is my marginal cost. And solving, I'll get a quantity of 170. Finding the associated price, that'll give me a price of 380. That's a problem because my monopoly price is 380, but everybody else has costs and the ability to price at 370. So the best I can do is set a price just a little bit below 370, right? And then I can capture monopoly profit, or I can capture the market as a monopoly, though I don't get true monopoly profits because I'm not pricing like a true single price monopoly. Then my question is, okay, well, this is a small innovation. What if they have a large innovation, defined and classed as the situation where the firm is now able to price like a true monopoly? So how low must costs go to be able to allow that to happen? So what I want to do is I want to say, okay, well, if this is my inverse demand, what's going to be the quantity that's going to correspond to a price of 370, which is everybody else's price? And then I'm going to want to be pricing just a little bit below that. So I set 370 equal to my, let's see, my inverse demand. And I found the quantity corresponding to this is 175. So what would be my marginal revenue if I produced 175? My marginal revenue if I produced 175 would be 20. Marginal cost must equal marginal revenue, right? That's the logic. And so my cost would have to be just a little bit below 20 to have it be optimal for me to produce maybe a little bit more than 175 and price a little bit less as a monopoly than 370 is the idea. Okay, and this is just checking that. So here's marginal revenue equals marginal cost, verifying indeed, yep, the quantity is going to be 175, and the price indeed would be 370. To be actually, if everybody else's, if my monopoly price is 370 and everybody else's costs are 370 to actually be a monopoly because they're standing by ready to come into the market, I'd have to price like 370 minus epsilon, so like 369.9 or something. Compute the price elasticity of demand at the price level and output that the firm will produce in part C. Is demand elastic or inelastic? So our formula for price elasticity of demand is dq dp times p over q. This is the slope, this is the point. The slope of my demand curve is this minus 1/2, right? Slope of the inverse demand curve is minus 2. We graph inverse demand curves, but we use the demand curve for elasticity. So my slope of my demand curve, Q solved for P, is 1/2 or minus 1/2. My point was, let's see, 175, and then, oh, this was, I wrote 340 here, but this was the point that I'm going to produce in part C was 370. So actually, what I want here is minus 1/2 times 370 over 175. And I'm going to bet, let me just verify that real quick. I'm going to bet that because I was not, when I wrote out this solution, I was copying it from a solution I had written out before. So let's see. Yeah, that's correct. Okay, cool. So, so this answer is correct. Minus 1.05, which is greater than 1 in absolute value. So this tells us we have elastic demand. And then for some reason, my solution has that same thing twice. Okay, so that was indeed the last page. Anyway, hope you enjoyed the video. Hope this helped you, and I'll see you next time.